Hey, what's up, guys? This is Chung here. So today, let's take a look at this 688 knight probability in chessboard. Um, I think this is this is a good question. Basically, you're just given like a 2D board, n by n chessboard, and the knight starts at uh, our rth row and sixth column. Okay, and then the knight will attempt to make exactly k movements. Okay, and the rows and columns are zero indexed, so the top left corner is 0 0. Okay, basically this is the one, right? And this is 0 0. Okay, and this is a n minus 1 and n minus 1. Basically, there are like n rows and n columns. As you guys can see, so a knight at any position, it can make like 8 possible movements. Okay, so basically each time the knight can make like a 1 out of 1 divided by 8 probabilities move, and then it asks you to return like after case movement, what's the total probabilities that the knight remains on the board. Okay, I mean, because if the board can jump in any directions, I mean, some of them are not valid. Basically, it will be out of the board. So the problem is just asking you to return the total probabilities after case movements where the knight is still on the board. Okay, so I think the first, I mean, this one is like a DP problem, right? Because, actually the state, what's going to be the state? The state is this. The state is like uh, at at case like at case step and like at row and column. That's the state. It's like a three-dimensional state, right? At case step and the knight is at like uh at the this row and column. If these three properties are the same, then we know, okay, we have seen this state before. Okay, and the value for this DP basically is a probability. Okay, it's a probabilities after case moves and the the ending at the position R and C, and what's the probability of that. Okay, okay, so so the first solution is like top down, right? Basically, we just follow what the question is asking us to do. Okay, I'm gonna do the first top down first. I mean, so that since it's like it's easier to understand. So basically, we're gonna have like a define like a DP, right? The DP like the current K, current row, and current column. Okay, how about this? And then okay, since we need the knight can at any moment can make can make 8 movements. I'm gonna define those 8 movements first. Basically, I start from it. I mean, the direction doesn't really matter, right? So basically, I start from this one. I start from here, and then I define this. I define this. Define this. I just follow the clockwise. I mean, you guys can do it whichever what whatever direct sequence you guys need. We just need to define all 8 directions here. So basically, the first one is this one. It's like we're moving on rows level. We are like -2 row, and on column level we do we -1 column. Okay, and then the next one is this one. It's this one, right? This one is like still -2 row, but +1 column. Okay, and then the next one is the -1 2 and then the next one is 1, 2, okay. Then keep going is 2, 1, and then 2 minus 1, and then 1 minus 2. The last one is minus 1 minus 2. Okay, sorry, minus 1 minus 2. Yeah. So, and then we simply return this. We return the at 0 row and column. Okay. And since we are like doing the DP here, I know I'm gonna define like this DP memorizations myself just to make this solutions language uh, agnostic. So if in mem, so we return this memorization, okay, this one, right? And then we have answer here equals to 0, and then we set these things in the end. I mean, this is just like template for the top-down DP. Okay, return answer. Okay, the okay, so I mean, at this moment, right? I mean, basically we have 4 directions. I'm sorry, we have 8 directions in moves. Okay, and then the new R will become to the current R plus D0. Okay, and the new C equals to the current column plus D1. Okay, and then since all the we just need to check if the new location is in the board or not. If not, we simply can abort. We can just ignore it, right? Basically, if the new R and N, okay, and 0. Same thing for the new column here. Okay. I mean, if that's the case, right? So the answer is what? Since we have 8 directions, I mean, so we have to accumulate all the answers from the 8 directions. Basically, what we have there, we have like a DP like new R, like new C, and the current, sorry, so K plus 1, okay, current K plus 1, okay. That's basically the DP, right? And okay, so that's the next step, right? But so after this, I mean, from the current one to jump to the to this state here, what's the probability, right? We have uh, 1 divided by 8, which is 0.125. Okay, right? So we just need to multiply whatever from the next step with the current probability to this state. Okay, cool. Yeah, so that's, oh, sorry. So the most important thing. So for the anytime for the top down, you need to define a base case. Well, so what's the base case? The base case is the current if the current k is equal to the k. Okay, because you know we are making case jumps, right? So basically we're starting from 0. Okay, and at the moment we're reaching k here, we know, okay, we have made case movements, and at this moment we need to return 1. So why 1? Because at the last moment, since we are doing like a multiply here, if we return 0, everything will be 0. But since we need a base case, right? The base case in the for the for anything that's we do a product, right? We need a 1 here so that we can have like a 0. We can have this like a 0.125 as a base case for the last movement. Cool. I think that should that I think that's it. Let's try to run it. Uh, uh, return double. What? 65? Uh, column. Okay, let me see here. Oh, sorry, here. Ah, what a stupid mistake here. Cool. So to accept it, let's try to run it. Yeah, so it passed. I mean, it's not that hard, right? It's pretty standard like DP problem. You know, you can call it like DFS. I think DFS is more appropriate. DFS with memorizations, right? Basically, you know, so the time complexity, of course, the time complexity is a combination of this, right? So basically, it's gonna be the n square times k, right? And then times what? Times 8, right? But since 8 is like a constant, so I think the total complexity is this n squared times k, right? And then the space complexity is also this. It's also like n squared times k. Okay, time and space. Yeah, cool. So I mean, it's pretty straightforward, right? Basically, we just uh, do a DFS, right, from the start to the end, and then but remember, so I think you just need to realize that. So with these three properties, you know, you can uniquely identify a state of this night movements here. And after that, it's just like for each of the movements, you just check if the move is valid. If it's valid, and then we try to accumulate that moves by multiply the current probabilities and with the next step. Okay, and then this is the base case, right? So we return one when it is still valid. Okay, cool. So that's that. I mean, so okay. So next, I'm gonna do the bottom up. So for those who are interested in the bottom up solutions, okay, you know, I think one of the advantage of the bottom up is that we can even like suppress, I mean, improve the space complexity from O(n) squared plus k to the O(n) squared because, you know, we're only relying on the previous step. Okay, so which means we can remove reduce one of the space dimension. Okay, so but let me try to implement the original versions. Okay, so for that we need this, and then we need the DP, right? So the DP, the first dimension is I mean, we're gonna have a 0. Okay, so start and n for this in range n, and we need another like layer of brackets. Okay, so basically this is how the Python define like three-dimensional of the okay of the list here. Okay, sorry. Okay. So I mean this n is pretty straightforward, but why do we do a k plus one here? This is because, you know, um, we need k movements, right? We need k movements, but but we still need like a base case for the k equals to 0. Okay, that's why we need that, because for the 0 we need set it to a base case which is 1 in this case, and then after that we need to make like case movements. That makes this DP total DP size like k plus 1 size. Okay, so same thing for this. So the first loop is a k range 1 plus 1 to k plus 1, and then j for I in range n for j in range n. Okay, you know, I think one of the difference between the top down and bottom up is, you know, for the top down, you know, it's easier. You just follow the step basically, right? You just follow the current step, and you all you need to care is that, okay, from the current step, what's the next step, right? That's that's the main thing you need to take care of for the top down. But for the bottom up, the bottom up, one of the essential like the essential, I mean, the nature of the bottom up is that you have to, I mean, start thinking in a different way. Basically, from the case step, I need to try all the possibilities of the I and the J. Basically, that's what this two for loop is for, right? I mean, at the step K here, I need to try all the possible locations on this board so that I can populate everything. But from this top down here, I mean, you you don't need to think that way, right? Because all you need to care is that, I mean, for the current state, right? What's going to be the next state? Okay, because this thing here, this recursive call is taking care of this nested for loop for you. But from the bottom up here, you have to be basically you have to manually try all the possible scenarios. Okay, from this 2D board here. Okay, and then here same thing, right? We're gonna loop through the moves here. Basically, from the current I and J location, let's say we have this is I and J here. So we need to think it in a reverse way. Basically, how how many ways we can get to the current I and J location. Same thing. There are eight ways, right? I mean, we can just reuse the same moves here. Even though like we're defining like this moves by going forward, but this move is bi-direction. Okay, so when moving forward, you can think it in a different way. Basically, if let's say for example, if we are like this is -2 and -1, so the opposite of that is the 2 and 1. Okay, right? So basically, even though we're thinking this like in the reverse way, right? How can we get the previously location from the current one? We can still use the same moves, this movement list here, because every two moves they are a pair, right? So it doesn't really matter. The sequence doesn't really matter as long as we have the same moves here. Okay, that's why we can just use the same moves here. And instead here, we have a new R here, right? But here actually what we're getting is the old I. Okay, it's the I plus the D0. Okay, and the old J equals to the J plus the D1. Okay, same thing. We have to check the validity of this old I and J. Okay, if the old I, okay, and same thing for the old J here. Okay, so then the current K, right? The current K and I and J plus same thing, 0.125 times dp k minus 1 and the old I and the new I, sorry, the old J. Okay, so that's that. And how about like the base case, right? Like I said, so the base case, what is the base case in our case? The base case is dp0 and this R and C. R and C equals to 1. Basically, without any movement, right? Our base case is only the R and C location is 1 because all the others they're all like invalid movements, right? That's why we just leave them at 0. All we care is that the starting point is 1. Similar like this one, right? I mean, so in the top down here, we're saying that okay, so the end point is one, but here like we're doing it like in a reverse way, right? Basically, the starting point is one. So okay, so that's that. And how about the final answer? Can we just return everything? Can we return the dp like k and then n minus one, n minus one? No, right? Because that stands for at the last step, at this position. What's the possibility ending at this position? But since we need to consider all the possible locations. That's why we need to accumulate everything together. Okay, for I in range n, and then for j in range n. Okay, and we have dp like k. Okay, because we're looking at the last step, right? Basically, for the last step, we need to accumulate everything from the last step, and that's gonna be our total. That's gonna be our final answer here. And again, so we're doing like this k, not k minus one, because we need to make k's movements. Since zero means we didn't move anything yet, right? So that's why we need to start from one to k to make k's movements, and the last one is the dpk. Okay. Uh, cool. Let's try to run this one here. Hmm? Oh, here. All right. So this one accepted. Let's try to submit it. All right. Also successful. I mean, same thing, same idea. It's just like from a opposite way of thinking of this problem, you know. So same thing, right? The time and space complexity is also same thing as the top down. They're both like n squared times m, sorry, times k. But like I said, you know, since all we need since the case statement only relies on the k minus one, we can like remove one of the dimension from our dp array here, and we can simply we can just remove this one here. We just remove the case here, okay, the case dimension, and here we simply remove doing this, and same thing here. But remember to do that, right? We need like a dp2 here, right? To rotate the current state and the previous state. I mean, it's similar like the 1D to compress the 2D to 1D to compress the three to from 3D to 2D. We just need to maintain like a 2D array. Okay. So same thing here, gonna be 0. Okay. Hmm. Start and for range. Or we can do this. I think we can do a dp dot copy. Okay, right? We just store the previously dp to this dp2 here. Okay. So I mean, so that here we can simply remove this one here. I mean, and then we remove this. But here, I mean, uh, so it's going to be a dp2 here. Okay. Because we are using like the dp2 is like the old dp, right? And this one here, yeah. So it means for that case, in that in that way, we don't have to reassign this one here. Yeah, and here we can simply remove this one here. Yeah, I think this should just work. Let's try to run this. No. Mm, uh, maybe this copy is not right. I mean, let's see. Hmm. Copy. Okay, so we have DP2 here. That's the old one. Okay, let me try this. I think there is a deep copy here. I think this should work. Hmm. No, deep copy. Okay. Okay. Fine. I'll just use the uh, brute force way here. So basically, I'm gonna define like, yeah, I don't know why this thing doesn't work. Maybe I did something stupid. I don't know. Hmm. DP here. So okay, DP2 here. Then in the end, I'll just assign the DP to the DP2. Okay, so let's run it. Yeah, cool. Submit. All right, works. I mean, I don't know why I don't know why this deep copy thing or copy doesn't work. Maybe it's still making a shallow copy. Anyway, so I just make like a new variables and then I just assign it. And in the end, I just assign this back to DP here. So basically, I'm rotating this like DP, this one DP, like by introducing a temporary like variable, similar like the 1D compression here. Okay, cool. I think that's it for this problem. I mean, uh, yeah, let me know what you guys think, and thank you so much for watching the videos, guys. Stay tuned. See you guys soon. Bye bye.